Here's a little trivia from geometry. The area of a parallelogram is just area equals base times height. Here's why that happens. Here's why that works. I've got a parallelogram here. If I take a section of this parallelogram and cut it off, I'm actually going to make a copy of this triangle that results from cutting that end off. And I'm going to move that piece over to the other side. And what that does then, if I've moved it, this is no longer here, is I've created a rectangle. And that rectangle has the same height as it always did. And it has the same base. The base used to go from here. Let me do that in a different color. The base used to go from here to here. And now it goes from here to here. But it's the same length. So the area of a parallelogram is the same as the area of the rectangle it comes from or that it can be made into. We also need to remember, though, that the area of a parallelogram is the magnitude of two vectors, the cross product of two vectors that make up its sides, as it were. Let me do my parallelogram in a different color here. Originally, I had this parallelogram in pink, and I turned it into the rectangle in white. If two of the sides of this parallelogram are vectors, then the cross product of those two vectors will be another vector, and it will have a magnitude. And the magnitude of that cross product is the area of the parallelogram. So it's fair to say that base times height is equal to the magnitude of the cross product of the two vectors. Let's call these vectors, call this one here u, and this one here v. So now what I've got is the cross product of u and v. But I'd also like to observe that the length of this segment here, the length of the base of the parallelogram, is also the magnitude of vector u. So instead of writing b here, I could write the magnitude of vector u. Let's do that. Magnitude of vector u, and I'll leave a space here, times something, is equal to the magnitude of the cross product of u and v. Now, if I look at this triangle here, and I say that this angle, the angle between the two vectors u and v, is theta, then I can say that the sine of theta is equal to, remember that this is the height of my rectangle and of my parallelogram, so I'm just going to call that height. The sine of theta is the height over the length of this line segment here, the hypotenuse of the triangle, but that's also vector v, and so the magnitude of vector v is going to be the length of that, the side of that triangle. And so multiplying both sides of this by magnitude v gives me an expression for height. So I can replace height. I'm not going to do it here. I'll have to write a new line here. I'm going to replace height, the expression for height, with magnitude v sine theta. And that's equal to the cross product of u and v. And this is actually the basis of the first, or one of the first geometric interpretations we had of the cross product. That formula was, I'll write it a little bit backwards here, a cross b, not the magnitude, just a cross b, is equal to the magnitude of a times the magnitude of b times the sine of theta times some normal vector n, the difference here being that this right-hand side is not a magnitude, it's a cross product, so it's a vector in and of its own right. When I look at, let's see, how do I compare these for you? this is also a vector here. So this is a scalar, and all of this is a scalar, and this is a magnitude, that's a scalar. So basically what I'm looking at here is a scaled vector in a particular direction. That direction happens to match the cross product here. So the difference is that this, if I took the magnitude of this side, since this is a normal vector, it's a unit vector, if I took the magnitude of this side, I'd be left with just this scalar. So this is kind of slightly in the wrong place in terms of which section or which video I've put it in, but it leads into something else, so I think it'll be okay. I just wanted you to see kind of some of the algebra that goes into where some of these formulas come from. Now, the nice thing about the cross product is that its magnitude also tells me the area of this parallelogram. Now, if I lay this out in R3, let's see if I can do this here. Years of practice. Okay, if I lay this out in R3, let's see if I can do the same or a similar parallelogram in R3. Let's say I've got a vector that looks like that, and maybe I'll just let the other one be the x-axis. Okay. What you probably can't see is when I undo an action, it doesn't show up in the way that if I write something and then I erase it, you can see me writing it, you can see me erasing it. But if I write it and then undo it, you don't see it at all. So there's a long gap. Sometimes it's because I'm undoing. Okay, so there is my, I hope, there is my vectors u and v. It's the same vectors u and v as I have up here. There's v, there's u. So that makes this v and this one u. And I'll note that this is theta. And then I have a parallelogram, or I can form the parallelogram that those two vectors sort of produce. Line's not quite long enough. There we go. Right, and that's the parallelogram, and I'll go ahead and color it in yellow again as well on this side of the screen, so you can see that's the same parallelogram in theory as the one above. What I want to look at now is something called a parallelepiped, which is a parallelogram in 3 dimensions. Each side is a parallelogram. Now they can be rectangles, but they don't have to be. The thing is, I really can't draw these, so I'm gonna stop my recording and go off screen and build it to the extent that I can, do the best job that I can, and then I'll come back. Okay, so as you can see, I've decided on a completely different orientation for this because I couldn't draw it any other way. But I will start by saying that the parallelogram that we saw in the previous sketch is this, the floor of this 3D object, the floor of this this solid, and the vectors that make up the sides of the parallelogram on the floor are here. That's my vector v, and here that's my vector u. But now I also have a third vector in the game. I guess I could call that one W. And I've messed up. I'm going to move the label for V because it's really kind of hard to tell. V is that vector there, W is that vector there, and U is that vector there. There is room, or there is capacity anyway, for a long argument about where this next formula comes from, but it's based on some similar ideas that we used in the argument for the area of a parallelogram, in that you can take this triangle off and stick it on the other side of it over here and just find the area of a rectangle instead. I'm not going to go into the detail of that argument because it is really quite lengthy, and I'm not sure that there's really a need for it at this point. But I will give us the formula to work with, and then we'll maybe take a look at an example. What we're looking at with this now is the volume of a parallelepiped. P-I-P-E-D. Very strange word. That volume is going to involve vectors W and U and V. And in this case, because of the way I've labeled these, it's going to be V first, and then U. What I'm going to do is take the cross product of V and U. That's going to be a vector. But then I'm going to dot that vector with this other vector W. I'm going to dot W with the resulting vector from this cross product. And that is going to give me the volume of this parallelepiped. Remember that dot products are scalars. So when I do this cross product, that's a vector. When I take this cross product, I'll get a vector here, and then I'll have a vector dotted with a vector, and that's a scalar. So I'm just going to get a numerical result here, and that's going to be my volume. Now I was careful to make sure that I gave you these vectors in the right order, because a cross product is not commutative. And if I use the right hand rule here, I need to point my fingers along the second vector. Yeah, I did get it backwards. Along the second vector in the direction of the first vector. Yeah, so I got these backwards actually. Let's change that to U cross V, because I want to make sure that my my thumb is sticking straight up when I do that, when I use that right hand rule, so that the height of my parallelepiped is going in the right direction. I don't want my height to be down here, because my parallelepiped, as I can see right here, is going up. As it happens, however, what we're going to do, because this is a volume, what we're going to do with this quantity once we find it is we're going to take its absolute value. Now, those are not the same as vector bars. If I talk about vector U's magnitude, I use that notation. If I want to talk about the absolute value of some real number n, and I use single bars. It's a slight difference, although sometimes you do actually see single bars as magnitude indicators as well. So you might, for example, see U with single. It depends on the textbook, depends on the author. I do actually like this distinction, because this tells me I'm in the context of vectors. This tells me I'm in the context of real numbers. So I would tend not to use this other notation for magnitude. It's not wrong. It is quite common, but it's not my preference. Anyway, so in this formula here, what I'm going to do is take the absolute value of the scalar that results from this multiplication. It might be slightly interesting to see where this formula comes from. So just in a very quick kind of rundown, I guess, I'll see if I can explain that a little bit. We can find the area of the base of this parallelepiped by taking the magnitude of the cross product of the vectors that make it up. And those vectors are lying in the xy plane. They're U and V. So I'm going to take the magnitude of the cross product of U with V. And because I'm taking the magnitude, that's a scalar. So I'll put that in parentheses. And then I'm going to multiply that by the height. Well, the height of my parallelepiped is, probably about that. And if I think about this possibly for a moment as a vector, then it might be clear that the magnitude of this vector is what we were calling the scalar projection of W onto, in this case, it's the z-axis. Part of the z-axis is this vector. And one way to get that vector, that big fat white vector there, is by taking the cross product of U with V. Because the cross product of two vectors is orthogonal to the plane those two vectors are in. And so these two vectors are in the xy plane. Their cross product will go up from the same common point, perpendicular or orthogonal to that plane. So that gives us the z-axis, or some part of it. And to get that, we take the cross product of the two vectors. So I'm going to call this white vector here. Let me erase a little bit of this stuff here. It's starting to get a bit difficult to see what's going on. I'm going to call this white vector here u cross v. It is the result of a cross product is itself a vector, right? So that's a little bit redundant notation, but that is a vector. And in order to find the length of that vector, I do what's called the scalar projection of w onto that vector, which is u cross v. So what I want here is comp, that's what we used for that, comp of w, the vector w, onto the vector u cross v. Well, the formula for comp, for scalar projection, I'm just rewriting this magnitude here. The formula for this is going to be w dotted with that vector, I'll come back to that in just a minute, divided by the magnitude of that vector, and I'll come back to that in just a minute. Just by our formula, we take the w and put it here and dot it with, and then we use this other vector in the other two positions, right? That's how that formula pans out. Well, that other vector, remember, is the vector u cross v. So I'm going to have u cross v in here, and I'm going to have u cross v in here. Well, the magnitude of u cross v, the magnitude of u cross v, those are scalars, those are just numbers, so they cancel, and they leave me with exactly this. Except that because our parallelepiped may be floating down into an octant down here, and since we're looking for volume, we're going to take the absolute value. So the punchline here is that the volume of a parallelepiped can be found using this formula. You have to note that the w vector here is the one that's, I don't know, sticking up away from the two that form the parallelogram base. The two that form the parallelogram base, this is the area of a parallelogram, right? The magnitude of this cross product would be the area of a parallelogram. So that's why we use those two vectors there, and then you dot that with the one that's sticking up away from those other two. So you could argue, for example, that this parallelepiped has other parallelogram bases. There's one right there in blue. Here's another one on the back in green. And there are three others. So it's not necessarily that you have to use vectors u and v in this position, but that if you use vectors u and v in this position, you have to use the third vector making up the parallelepiped in this position. If you use w and v using this parallelogram, and you use this as your height, right, then you have to change the order of the vectors in the positions that the vectors, the roles that they play. One last observation here. We have been playing around with this thing, this dot product of one vector and the cross product of two other vectors, this also being a vector. But it has a name, and it's called the scalar triple product. The scalar triple product of three vectors is just for those three vectors, I've chosen the vectors a, b, and c here instead of u, v, and w because we already used those. A dotted with the cross product of b with c. So this thing that we've been playing around with just has a name, I guess, is really what I wanted you to see here. And it's the it's the scalar triple product. Let me fix that. The scalar triple product, the dot product of one vector with the cross product of two others. Now here's an interesting thing. If I took this vector W here and I rotated it so that its initial point was still located at the origin, but its terminal point, came down here. And in fact, let's take it all the way down so that it's on the XY plane with the others. I think I'll use a blue one here. So if I move W so that it's down here on the XY plane with the vectors U and V, this is my new W, I'll call it W prime. If I do that, then guess what the height is going to be? Guess what the scalar projection of W onto this cross product is going to be? It's going to be 0, right? So this whole computation here, this whole scalar projection value will be 0. So I'll be multiplying something by 0. And that is going to tell me that the volume of the parallelepiped is 0, but it tells me something else. If the volume of the parallelepiped is 0, then one of two things has to happen. Either the magnitude of the cross product here is 0, which means there's no height to this vector, or this value is 0, which means that there's no height to the parallelepiped. That would happen because the third vector, this vector W here, was on the same plane as V and U. So if the volume of the parallelepiped, if you do this work here and you get 0, then what it tells you is that U and V are on the same plane, but so is W. It tells you that all three of these vectors are on the same plane. We say that they're coplanar. I'll just write that down. Coplanar. This happens when the scalar triple product is 0. Oops, not theta. When the scalar triple product is 0, then the vectors are coplanar. So it's another little tidbit that we can take away from this particular conversation.